Welcome to a new lecture on flexibility matrix method. Today we are going to discuss about force transformation matrix, small letter B. So it is a matrix connecting the external forces with the internal forces. External forces means structural level approach, that is structural forces. With the internal forces means element forces. So we know we represent the ex- external forces by the capital letter R and element level forces by capital letter Q. And system displacement or structural displacement by small letter R and element displacement by small letter Q. So force transformation matrix can connect internal force with external force, and hence it is written as a matrix form Q is equal to B dot R. Similarly, a quick recap of fourth module, stiffness matrix method, in which we studied displacement transformation matrix. There we discussed small letter q is equal to a dot small letter r, connecting element displacement with a system displacement, where a is called as displacement transformation matrix. Displacement transformation matrix. Yes. So force transformation matrix connects external force with element forces. So when we apply unit external force, the corresponding internal force is called as force transformation matrix. When I apply R equal to 1, Q is equal to B. So when I apply unit system force, the corresponding element force is called as the force transformation matrix. That is also another definition for force transformation matrix. So example 1, consider the structure as shown in figure. It has three loadings or three external load R1, R2, R3. So system coordinates I can define at the point where load is applied because nothing else mentioned. So first system coordinate, second and third, three system coordinate. We can split this structure into small elements as three span structure. That is first span, second span, and third span. So three elements and six element coordinates. That is, we consider it as a beam element having beam moment coordinates. So 1 dash, 2 dash, 3 dash, 4 dash, 5 dash, 6 dash. Now, force transformation matrix we are going to derive or we are going to calculate. So first procedure is that we have to apply unit system force. Unit force at first system coordinate, and then find the corresponding values of the element forces at each point. There are 6 element points, right? We have 6 element points and we are applying a unit load R1 equal to 1 at the first system coordinate. So we will get 6 values. So B11, that is force at 1 due to system force at 1. And what is B21? B21 is element force at 2 due to system force at 1. System force at 1. That is unit system force at 1. So apply R1 is equal to 1. Then how will I calculate the element force? Just to take the bending moment diagram here. In displacement transformation matrix, we took the displacement values. Here in force transformation matrix, we will take the bending moment values. That is moment value. Moment is nothing but a force. So 1 into L, force into perpendicular distance is L itself. So L is the bending moment value, M value at this point, and we have to consider its direction. This load will produce a clockwise moment and an anti-clockwise moment is developed here, that is L. So its direction is anti-clockwise, hence it is shown here. You can just draw the line from the baseline to the bending moment. So it is anti-clockwise and hence we give a negative sign anti clockwise, hence minus L. And at the second point, no bending moment, so 0. Third point, nothing. Fourth point, nothing. Fifth point, nothing. And sixth point, nothing. No values exist. So minus L 0, 0, 0, 0, 0 is my force transformation matrix due to first condition. Now second condition, apply unit force at a second system coordinate R2. R2 equal to 1. I apply, I get the bending moment diagram. Force into perpendicular distance L, L, hence a 2L bending moment. At this point, I will get L. It is anti-clockwise. That is, it will here it produces a clockwise. Here it will try to oppose the load. So anti-clockwise is being produced. That's been shown. Or you can just simply take it from the baseline to the BMD value. Basic understanding is you can consider this way and draw it above. Okay, that's why I draw the bending moment diagram above this line because this is anti-clockwise. So this is minus 2L clockwise L minus L 0 0 0. Next unit force at a third point, you get the bending moment diagram anti-clockwise minus clockwise 2L, anti-clockwise minus 2L, then L, a minus L, and then 0. This is, and then finally adding up all these three, I get a matrix consisting of R1, R2, and R3, and this is called as my force transformation matrix represented by letter small letter B. It is actually force transformation matrix represented by letter B, not A. Okay. In second question, find the deflection at the free end. So first consider the system coordinates. It's been asked find the deflection at free end, but here there is we have to calculate delta C equal to question mark, but no translational system coordinate act at that point or no translational load act. So we consider a dummy load R1 to act at that free point. Only then we can calculate this delta. So R1 equal to 0. A dummy load in translation direction is being considered. So total there are two system coordinates R1 equal to 0 and R2 equal to 0. R2 equal to 20 kilonewton meter, which is given in question 2. So we got two system coordinates 1 and 2. Next step is element coordinates 1 dash 2 dash 3 dash 4 dash. That is at the point joint B, the moment of inertia value changes actually. So that point there is a change in the material property, change in material property. Hence, we need to consider that point where we split the section or we split the structure. So this will be my first structure. This is my second element. So two elements are considered and its element coordinates are marked. Now we find out the element flexibility method matrix. That is element flexibility matrix. General formula is L by 6EI 2 minus 1 minus 1 2. Apply the length and EI values. For the first element, the length is 2 meter. So 2 is applied and EI value is 2 EI. Hence it is 6 into 2 EI. 2, 1, 1, 2. We'll get 1 by 6 EI, 2 minus 1 minus 1, 2. Then second element, apply the same concept. Length is 3 meter. EI is EI itself, 2 minus 1 minus 1, 2. Take EI inside, get it as 1 by 6 EI, 6, 3, 6 minus 3 minus 3, 6. Taking 1 by 6 EI common outside, I write the assembled flexibility matrix as 2 minus 1 minus 1, 2. 6 minus 3 minus 3, 6. This will come here. And the previous one, this will go and place it here. We assemble that one in a diagonal direction. Here other terms are 0. Next, force transformation matrix. Apply unit load at R1 at the first system coordinate R1 equal to 1 and correspondingly find bending moment diagram. That will be total 5 meters. So here is 5, anti-clockwise, so minus 5, minus 5. Then clockwise 3, then anti-clockwise minus 3, and at the fourth point it is 0. So the B matrix will come up with minus 5, 3, minus 3, and 0. Apply unit load at R2. It is a moment at any section. I take a section and look at this side, the moment value is 1 itself. I take a section here and look at that side, it is 1 itself. So this is my bending moment diagram. 1, 1, 1. Anti-clockwise is taken as minus, clockwise 1, anti-clockwise minus 1, and clockwise 1 itself. So finally adding all the metrics together, I get the force transformation matrix as shown in figure. Now the next step is you have to study this formula, system flexibility matrix FRR equal to BR transpose dot F dot BR. BR, the suffix R is used because we are dealing with a determinate structure. If there is a redundant structure, we will use another formula or another symbol. That's why. So it's a determinate structure. So system flexibility matrix can be calculated BR transpose dot F dot BR. So we got B, take its transpose, change its row and column. I get the B BR transpose into F matrix into B. Use calculator, directly substitute, and I will get a FRR, that is system flexibility matrix. Then element displacement is FRR dot load matrix R. So while using calculator, you can define all the four matrices together. That is, you can define this as matrix A, B, B, C, and then load matrix as a D matrix. And then while calculating A into B into C, you get FRR, then multiply it with the matrix D, you will directly get the value of element displacement. FRR dot capital letter R. That is capital letter R load matrix. Load, we can see in the question, we consider two system coordinates. First system coordinate is R1, that is in translation y direction or downward direction. It has no load in the question, hence the that is a 0. And in the second R2 is a rotational, its value is 20, hence I write as 20, that is my load matrix R. Substituting, I get the final answer as 170 by EI and 80 by EI. So deflection is asked, hence the final answer is 170 by EI. Now, next question is a simply supported beam condition. Let's see. Find displacement at center of beam. So question itself shows two loading condition, 10 kilonewton and 2 kilonewton meter. So we consider two system coordinates, one R1 equal to 10 kilonewton, that is translation, and second one is rotational, that is moment coordinate 1 and 2. And the load matrix will be first one 10 and 2. Load matrix as 10 and 2. Second step is element coordinates. We split it into, since we have to find the deflection of the center point, this one and this one. We consider that it as two element coordinates. Two elements, and each element will have two element coordinates, hence total four element coordinates. Element flexibility matrix, combined flexibility matrix F1 and F2. L by 6 Ci, length is same, hence we take it commonly outside, we'll get it as 1 by 2 Ei, 2 minus 1 minus 1 2 0 0 0 0 0 0 2 minus 1 minus 1 2. Same procedure, same step. Next step is force transformation matrix. I apply R1 equal to 1. First apply R1, then find the BMD. BMD is WL by 4. This is a downward. Here rotation is allowed. Hence what happens? Two moments like this is produced. Then only this will bend like this, right? So this is downwards. Hence from the baseline, I drew the bending moment diagram downwards. Only then I will get a clockwise moment here and a anti-clockwise moment there. So apply unit load at R1 equal to 1. Draw the BMT at this point. The value is 0, here also 0, so no moment is being resisted, but at the center point you have a bending moment value WL by 4, that is 3 by 2. And for B21 it is anti-clockwise, hence minus 3 by 2, but for B31 it is clockwise, hence 3 by 2 as 3 1, yes. And B41 there is no moment being resisted and it's 0. Next, apply unit load at R2 equal to 1. Draw the bending moment diagram. The BMT would look like this one. At this point, there is no moment, so it is 0 at both ends. And after calculating, finding the support direction RA and RB and drawing the BMD, you will get the bending moment diagram like this with the values 1 by 2 here and 1 by 2 here, both in clockwise direction, and hence my B22 is 1 by 2 and B32 is also 1 by 2, both clockwise and hence taken positive. 1 by 2, 1 by 2 positive. And next step is system flexibility matrix, br transpose dot f dot br. Adding it in the calculator, we will get the value of FRR. Then element displacement, or no, system displacement, small letter r, equal to FRR dot capital letter R. That is equal to, just substituting it with the load, multiplying it with the load matrix, I will get the value of R1 and R2. That is my system displacement values. This is the way in which we